work on things that they have a
I'm not, so I told her I would be there. I had to email her back and said, no, It's high level, like a world WMO kind of meeting with other people that steps in certain things.
Okay. Welcome everyone to another seminar. Today we have another duo, and it's a pleasure for me to introduce them. So the first speaker is Stephanie Henderson. She earned her PhD in atmospheric science from Colorado State University. In 2019, she started working here at University of Wisconsin-Madison as an assistant professor. Her research interests are focused on understanding the atmospheric processes that occur in subseasonal timescale. And our second speaker is David Henderson, and he also received doctorate in atmospheric science in 2017 from Colorado State University. And now he is working as assistant research at the Space Center and Engineering Center. So today they will be talking about dissecting Madden-Julian Oscillation teleconnections. So without further ado, this is all yours.
Thanks, Kari. All right, hi everyone. So thanks for coming. We're kind of going to go back and forth with this talk. It's kind of fun because it's a project that we've been working on that combines our expertise. And we are going to be looking at the drivers of MJO teleconnection patterns. So particularly the contributions of different sources of heating. This will be a nice application of satellite data to try to understand MJO teleconnection patterns. Can everybody hear me? Am I being loud enough in the back? Okay.
I can agree.
Okay, thanks. So first, I'll just introduce the MJO for those of you that are not too familiar with it. So this is a typical MJO event. And what's shown there in the colors is precipitation from TRIM. So the blues are showing enhanced precipitation, the reds are suppressed precipitation or anomalously last precipitation. And what you can see is that during an MJO event, and you can see that the days going forward here, MJO convection initiates near the Indian Ocean, and then is preceded by suppressed convection. And then that convection will propagate eastward over the maritime continent and into the Pacific, where it becomes decoupled to convection. Right, and that's preceded and followed by suppressed convection. An MJO event typically lasts around 40 to 50 days. And because it is an eastward propagating system, we often will separate it into 8 phases, where each phase tells us where the MJO convection is at any point in time. So MJO phase 1 is when we have that enhanced convection in the Indian Ocean, and then by MJO phase 8 is when that enhanced convection has reached the Central Pacific. Right, so it's just telling us where the MJO convection is at any point in time. So MJO convection, MJO acts as a heat source, which triggers Rossby waves. And you can see kind of as an idealized picture here on the left-hand side, where we have upper level divergence associated with these tropical systems that will force Rossby waves that propagate away from the tropics and significantly impact the extratropics. Here's a specific example to the MJO. This is for MJO phase 3, so you can see that that's when we have the enhanced precipitation over the East Indian Ocean and suppressed precipitation here in the yellows over the Western Pacific. And associated with that is this Rossby wave train, which we refer to as a teleconnection pattern, that propagates, you can see kind of the makeshift arrow that propagates over the Pacific and over North America and beyond. So this has really large impacts on the circulation in interseasonal timescales. Each MJO phase lasts about 5 days. So this is giving us weekly predictability. Why is this important? Well, these teleconnection patterns have a lot of impacts. So for example, MJO teleconnections are known to impact blocking patterns. So everywhere you see a little omega symbol, it's talking about where blocking patterns are impacted. It impacts atmospheric rivers, which is really important for precipitation. It impacts monsoons, impacts hurricanes. It has many global impacts, making teleconnections really important to understand. So that means we want to make sure that MJO teleconnections are properly captured in our models, right? In order to get appropriate MJO teleconnections, then we need to have multiple aspects that are well captured within models, including the MJO itself. So this slide here, this is from a paper that I did back in 2017. And this is using CMIP5 models. And we looked at the relationship between how well a model simulates an MJO and the basic state, and how that relates to how good the teleconnections are in the first place. And what we found is, if you look here on the left-hand side, this is a measure, east-west ratio is a measure of how well a model propagates its MJO eastward, because not all models have an eastward propagating MJO. So here's observations, is this dashed line here, and each of these circles are individual models. The models that were deemed to have a poor MJO are in the open circles, whereas the ones with a decent MJO are in the filled circles. On the y-axis here is a pattern correlation with the MJO teleconnection. So we use it as a measure of, well, how well does this capture the MJO teleconnection patterns? Does a good MJO necessarily mean better teleconnection patterns? And the answer was not always. Sometimes we saw really high, really decent MJOs, but really bad teleconnection patterns, right? Some of the poor MJO models were doing just as bad as some of the good MJO models at getting MJO teleconnections. A lot of that was because of the basic state, how well the basic state was represented. That's what this figure shows, but I'm not going to talk much about this for this particular study. But one of the things that we couldn't do in that work was better understand why you would have situations in which you would have a decent basic state. So like the subtropical Pacific jet, the waveguides are well represented in the model, but you would have very poor MJO teleconnections in certain models that had, so for example, this pink circle here had a decent basic state, but its MJO teleconnections were just as bad as some of the poor MJO teleconnections, right? So there's something still different here that we weren't able to measure at that point. So if you go on, so this is a big deal, and this is a big deal because not only for understanding MJO teleconnections and why do some models have good MJO teleconnections and some of them have bad MJO teleconnections, but there's also a lot of uncertainty as to what's going to happen to the MJO in a future climate. And if there's a lot of uncertainty as to what's going to happen to the MJO, then there's a lot of uncertainty as to what's going to happen to MJO teleconnections. Right, so this is showing the changes in the projected changes in MJO precipitation. And you can see that these error bars or these uncertainty bounds are really big. We don't really know. If you spread it out by longitude, we know even less. Is precipitation going to increase or is it going to decrease? There's a lot of uncertainty associated with what's going to happen to the MJO. And so there's a lot of uncertainty with what's going to happen to MJO teleconnections. And it doesn't help when we can't get MJO teleconnections right in our models in the first place. So there's been a recent push to develop process-oriented metrics to diagnose MJO teleconnection biases in GCMs. The better we can understand what makes a good or bad MJO teleconnection pattern, then the better we can work to represent them, and the better we can understand, how things might change in the future. Okay, so we wanted to figure out how to better diagnose MJO teleconnections. And what we wanted to do that we weren't able to do in that 2017 study was to look at the heating. So for decades, a lot of the classical Rossby wave theory research used these really simple models in a thermal forcing to figure out what the atmospheric response is to diabatic heating. Right, so if you take some heat source, such as the MJO, and you put it into a simple model that's where you solve the steady linear equations about some mean state, some mean flow, right, or basic state, then what you get is the response, the circulation response to that forcing. This was used a lot to understand Rossby wave theory. A way to look at thermal forcings is using the apparent heat source. This equation here by Yana et al. 1973. So you can see that equation there below. Now in red here, this is a way to get at the apparent heat source using a residual of the dry static energy budget. So this is really nice for using reanalysis as a heat source, because all you need are the winds and temperature to get dry static energy. So for that 2017 study I mentioned earlier, that's what we used as truth, right? This is what we said, well, this is what MJO heating looks like. That's what we had easily available, right? It's very convenient. However, we can't decompose this. We can't separate this in ways that let us understand the differences in the heating. For that, we need the right-hand side of the equation. Right, so the right-hand side of the equation separates out the components of the apparent heat source by the heating that's due to radiation, right, so radiative heating, the latent heat release, which is in blue, and then this last term here, which is the vertical eddy transport of sensible heat. Right, so it is this right-hand side of the equation that we are going to be using in order to dissect teleconnection patterns and understand the role of heating in driving teleconnection patterns. And with the goal that we can use this to better diagnose models and how well heating, or how well the MJO is simulated in models as it relates to the heat source and the clouds that they have.
So then I'll take over here. So what we want to do is be able to use observations and satellites to best understand what these individual components are. And so we have radiative heating, which is strongly dominated by clear sky and cloud effects. And so for that, we're going to be concentrating on using data from the CloudSat mission. And then we have latent heating, which is generally derived from precipitation processes, condensation of water. And so for that, we're going to be using data from the TRIM and GPM missions. And really, the importance of these are that within the A-train data for CloudSat and Calypso, we have active sensors of LiDARs and a vertically pointing cloud radar from CloudSat. And so what this does is the cloud radar is sensitive to cloud ice and cloud droplet particles within the atmosphere, and the LiDAR is also very sensitive to optically thin clouds and can see clouds within the boundary layer that are within the radar clutter region that CloudSat might not be able to see. And then couple that with information from MODIS to help constrain other cloud properties, we can use these together as a suite to understand the vertical resolved cloud drops within the atmosphere to understand the cloud component. The tropical rainfall measuring mission, the total precipitation mission, the core satellites have a downward pointing precipitation radar. So these frequencies that the radars are tuned to are very sensitive to precipitation particles, but not clouds. So they can't see the cloud component, but they can see the precipitation component. And so we can use algorithm retrievals from these two different satellite missions together in concert to derive what are the clear sky and cloudy sky radiative portions, and then what are the precipitation portion for latent heating. So to do that, we're going to use two specific products from these individual satellite missions to derive these. For latent heating, we're going to use the convective stratiform heating product. which provides profiles of latent heating from derived lookup tables. And so I'll talk about in a little bit of how those are derived. And then from CloudSat, we're going to use a product that I helped develop called 2B Flux Heating Rates LiDAR, which uses the information from the A-train to give us vertically resolved radiative flux and heat estimates within the atmosphere. And kind of these first two top figures here are kind of the two phases we're going to be talking about throughout this presentation. So we combine the phases together to increase our sampling to better understand these processes. So we're looking at MJO phases 2 and 3, and also phases 6 and 7 together. And the reason these are often studied, and correct me if I'm wrong, but they have opposite patterns. And so in phase 2, 3, over the Indian Ocean, we see more active convection in the MJO, and in phase 6, 7, we see more suppressed. And so it's good to look at these different teleconnection patterns together because of their opposite side. So for vertically resolved latent heating, we're using, like I said, the convective and stratiform heating data set. And these really aren't complicated data sets to use. They're derived by looking at field campaign data and using cloud resolving model simulations to look at what the different vertical latent heating profiles are as a function of height and precipitation intensity. And then these are further tuned by using field experiment data. So on the left-hand side is an example of convection latent heating lookup tables. We have precipitation intensity here and then height here. And then on these right two panels, we have just an example of what a latent heating profile would look like for convection as a function of increasing intensity. And then using one of these convective profiles, what it would look like if you increase stratiform heating. So you can see it goes from a more convective profile, and as you go to more stratiform heating, you see the heating increase in the upper levels, and you have evaporation below the stratiform deck, which leads into a cooling. I will mention that there are many, many ways and many different products to derive latent heating. There's a lot of debate of whether these are right in specific regions because of different dynamics and cloud properties and precipitation properties. But the main reason we're using this is because for trim and GPM, this is the most updated and state-of-the-art thing they have for their products. So we wanted to be consistent with what was the most latest release for latent heating. For radiative heating, we're using the radiative heating rates from 2D Flux Heating Rates LiDAR from CloudSat. In general, as I mentioned, we can use combined information from the Calypso LiDAR and from CloudSat to derive the location of clouds within the atmosphere. So in this top hand, we have some output from Flux Heating Rates LiDAR of vertically resolved optical depth product that we have, where you can see we have an optically thin cirrus cloud that would be detected by the LiDAR, some lower level boundary clouds that would be detected by the LiDAR, and then also clouds detected by the CloudSat radar. And we have individual products that are specifically made for looking at cirrus clouds and their properties, and then also the cloud water content, precipitation water contents, and their effective radius from other CloudSat data sets. So by using these vertically resolved cloud properties, we put them into a vertically resolved radiative transfer model that has 125 levels at 240 meter resolution. We run that for shortwave and long-wave radiative fluxes, and that outputs vertical profiles of radiative fluxes, heating rates, and then optical depth as well. And really the important thing with this whole process is we run the radiative transfer model 2 times. The first with all cloud properties involved with it, so we can see what the cloudy signal is within the profile, and then we run it again with the clouds turned off, so only clear sky only. And what this allows us to do is to, for each individual CloudSat observation, explicitly understand what the cloud radiative impacts are for each individual profile, but then also understand what the clear sky radiative impacts are. So why do we care about radiative heating in general? And so throughout this talk, you're gonna see that we're really focusing on the radiative heating component more than the latent heating component, because a lot of recent studies have really been understanding how anomalies and cloud radiative heating can actually have substantial impacts on local circulation patterns. So this was a study I was a part of from Yoon Kong in 2019 when she was doing her PhD here. And what we showed from this is that if we look at the radiative heating within the atmosphere, really the main contributors were upper level cirrus ice clouds, low level liquid stratocumulus clouds, and what we're calling multi-layered cloud structures, which you can think of as an ice cloud with a liquid cloud beneath it. And it was really the balance between these individual components that when you looked at their anomalies between the northern hemisphere and the southern hemisphere had a really big impact in radiative imbalances or driving energy across the equator. So kind of a main thing I want to show here from this study is when we looked at hemispheric imbalances, is actually the cloud radiative heating portion was 3 times larger than the imbalance with latent heating. So while latent heating can be larger magnitude locally, the anomaly in cloud radiative heating was much larger between the hemispheres and which was a much more important component in driving hemispheric imbalances. And these were heavily driven really by the balance between heating and ice clouds in the tropics and the southern oceans in mixed phase clouds. So any perturbations in those clouds could have substantial impacts on the transport of energy across the equator and therefore the circulation. And I'll just briefly mention, it's maybe kind of hard to see these studies down here, but in 2 recent studies, one from Jen Kay looking at the impacts of the southern oceans in mixed phase and liquid phase clouds, they found that the more you increase the amount of liquid water within the GCM, so essentially showing that they usually have a high ice bias and not enough liquid water in the mixed phase cloud portions, that you actually saw a significant cooling within the southern oceans due to the increase of radiative cooling in those mixed phase clouds, which actually led to a strengthening of the southern jet and actually a polar shift of the southern jet. So not only, it was just a simple change from the mixed phase clouds and liquid clouds that actually gave a more realistic signal in the jet. So any change between high-level clouds and those mixed phase clouds could actually have implications for the local circulation in the southern oceans. Another one from Lee et al. With Dave Thompson's group at Colorado State looked at the impact of anomalous heating from cirrus clouds within the tropics, seeing that in future climates, because of warmer weather, cirrus clouds could occur higher in the atmosphere. That changes the baroclinicity from the tropics and mid-latitudes, and that actually just those cirrus cloud anomalies alone from the increases of heating higher in the atmosphere could actually shift the mid-latitude jet in the northern hemisphere more polar by a substantial degree, which is really the weather that impacts us the most here in the US. And so, again, anomalies in cloud radiative heating were the main factors that led to these circulation changes. So what do radiative heating anomalies look like? As I mentioned before, the cloud radiative effect that we're looking at is essentially the difference between effluxes or heating with or without a cloud within the atmosphere. And so this is a nice diagram that I took from Hong from her dissertation that kind of shows the multiple ways that radiation can interact with clouds. I think kind of the 2 classic things that we think about in terms of cloud effects are these left 2 components. If we think about low-level liquid clouds, they're really bright, they have a high albedo, they reflect a lot of shortwave, they tend to cool the planet, whereas the long-wave component is not as impactful in terms of that. And also, high-level cirrus clouds can let a lot of shortwave through, but they're really efficient at trapping long-wave energy, so they tend to heat the planet. Well, using the observational data that we just talked about, we can actually show what those look like in terms of a cloud heat anomaly. So if we think about the thin ice cloud signal here, these are zonal mean plots of cloud faction and associated radiative cloud heating anomalies. Here's a cloud faction for upper level single layer cirrus clouds and their corresponding heating anomaly. It may be kind of hard to see here, but there's actually some blues at the top of this showing long wave cooling above the cloud tops. There's actually heating here, which is the little bit of shortwave absorption we get at cloud top. And then a substantial amount of heating below these cirrus clouds due to the greenhouse effect, so they're warming the planet. And then the stratocumulus clouds is really the long wave impacts that are affecting these clouds, where we see substantial long wave cooling at cloud top, and then the intense long wave emitted back to the surface, we see long wave heating at the bottom surface. So using these observational products, we can begin to dissect specific heating signals. So we can kind of walk through how this looks like from the global level and then begin to narrow it down for how we do it with the MJO. If we bring back our equation, we have Q_R plus latent heating is giving us our Q1. Here is the zonal mean net radiative heating, so short wave plus long wave for all sky cases. So this is clear sky plus cloudy sky from CloudSat. And then the zonal latent heating that we get from GPM. And what we can do is then we can take our radiative heating component here on the left. And again, as we mentioned before, with our retrieval, we do clear sky and cloudy sky individually. So we can separate this all sky into its clear sky component and its cloud component. And again, if I pull up the global mean cloud fraction, we can again see those same signals. We have a lot of cirrus in the tropics, which leads towards our greenhouse effect, and we can see again the signal for our low-level stratus clouds appearing here near the poles in the cloudy sky impacts. But then we can take this even a step further, and we can look at individual cloud elements then as a function of cloud phase. And so instead of looking at specific clouds, we're switching this to more of a phase, because it's much simpler to compare model cloud properties as a function of phase than it is an altopenus cloud versus a cirrus cloud. It's much easier to use phase as a prognostic variable in comparing models. So we can take our cloudy sky function and split it into cases where we have single layer ice clouds only and their respective cloud fractions. Liquid containing clouds, this would be liquid or mixed phase clouds, and their respective cloud fractions. So in the tropics, what we'll be talking about, mixed phase clouds are generally speaking of deep convection. And then multi-layered cloud structures, which we have a cirrus cloud over a liquid cloud. You can think about it in that kind of way in the tropics. And these multi-layer clouds are really important in terms of the vertically resolved data that we have, because passive sensors a lot of times can't see below this top level cloud. So there's a lot of cloud information that can be missed by looking at passive sensors. And models, because of parameterizations, can generally struggle to capture these multi-layer cloud structures. So if we kind of bring back our total P1 equation, we can kind of expand it to this thing that we have latent heating from trim, plus the clear sky portion that we get from fluxing rays LiDAR, and then plus the sum of the conditional mean of each individual cloud type times their cloud fraction can give us the total Q1 profile. And the interesting thing about that is then we can tweak and look at what would the anomalous heating signal look like if we removed fluid clouds or if we removed ice layer clouds. How would that impact our teleconnection patterns? So this is what that same process looks like for the MJO. So here's for phase 2 and 3, latent heating, the clear sky radiative heating, and cloudy sky on the bottom. And on the right-hand side is when we add all those components together. Now this doesn't look like much here. You can see where the latent heating signal dominates and the clear sky cooling of the long wave in the atmosphere dominate. But again, when we look at the anomaly, that's where things shine between radiative heating and latent heating. So to derive these profiles, we did 5 years of CloudSat data that were composited for each individual MJO phase over extended winter. So November, December, January, February, and March. That's how we did that. But then we can also then subtract the extended winter climatology for that same period to derive the MJO anomaly, which is what we have here. So here is the anomaly of latent heating, cloud radiative heating, and then the total Q1 on the bottom here. And you can very easily see the active versus the suppressed phase of the MJO in these for both the radiative heating and the latent heating signals. And I'll even just point out here, I actually skipped this one in case it's hard to see in the back. I'll put the total P1 on the top here. You can see how the radiative heating is really filling the gap of all this upper level heating that we missed if you use latent heating by itself. And then kind of for the final thing, these anomalies are what we're going to be putting into the model. That stuff we'll be talking about next. We can take that same signal and then dissect it again by their individual cloud types. And then here's kind of a fun animation of showing the individual cloud types and their cloud fraction anomalies for each individual cloud phase that we'll be using for the model experiments.
Okay, so in the same way that all of our original Rossby wave studies looked at to understand the Rossby wave response to heat sources in the tropics, we're going to do a very similar thing. We're going to use these simple models. We're going to use a simple model, which is specifically known as the linear Baroclinic model, or LBM, and we're going to input a heat source and see what the response is to the heat source. So this is the model that we're using for this. It essentially just calculates the linear response to a prescribed forcing, where the prescribed forcing would be our apparent heat source, right, or heating. taken from our observations. And this model uses the hydrostatic primitive equations on a sphere, and they are linearized about a mean state or a basic state. We use the exact same basic state for all experiments, which is just a boreal winter mean. So it's going to have the winter mean fields that will determine the Rossby waveguides. So the only thing that we're changing for all of the experiments that we're going to show is the heating, is the forcing. And I'm going to be primarily focusing on the response in the Pacific because MJO teleconnections behave very linearly in the Pacific. So they are very well captured by just a simple linear model. Beyond that, nonlinearity is becoming important. So that would not be captured by this model. So for example, the Atlantic response and so on, you would need nonlinearities in order to get accurate representations. But this, using a simple linear model, is a really nice way to get an attribution, right? Because everything is linear. So I'm going to show you these experiments first that you see down here, where we do an experiment, which we're calling the Q1 experiment, using Q1 anomalies, which consists of anomalous latent heating from the CSH product, and also the cloud-sat radiative heating. Then I'll show you just the latent heating anomalies, so there's no QR. And then a QR experiment where we have no latent heating and just the cloud-sat QR anomalies. So let's start with this figure, which I just showed you in the last slide. What you're going to be seeing are anomalies in the 500 millibar geopotential height. So what you see here is, in the black contours, is the 500 millibar geopotential height response to MJO latent heating anomalies for MJO phases 2 and 3. So that would be, the contours are when you just use this as your forcing, which is our MJO latent heating anomalies. And what you see is that you get, a magnitude of this anticyclonic anomaly of up to around 30 meters. Versus if you force it with radiative heating, right, so this becomes our forcing now, what we get is what you see in the color shading. And if you compare the magnitudes here, this goes up to around 14 meters. So that's 50%, that's half the magnitude, right? So QR is about half the magnitude of the response to latent heating anomalies. That's not negligible, right? Oftentimes when we think about teleconnections, our mind automatically goes to the latent heating. Well, the latent heating forces these teleconnections that we see, but these are the magnitude of the response forced by latent heating versus the response by the QR are not significantly different, right? It's half the magnitude, which is not negligible. If you go to the next slide, we can compare that to the full Q1. So QR again is in the shading, same as you saw last time, but now the black contours are showing the Q1 experiment, which includes latent heating and radiative heating. And you can see that we get a maximum magnitude around 40 meters. Right, so comparing 40 meters to around 14 meters, that's a quarter of the total response. That is entirely from radiative heating. That is substantial. Right, so radiative heating is also important, right? Not just latent heating. Do we see this for other MJO phases? Yes, we do. So this is for MJO phases 6 and 7. So here at the top, you can see, again, for the QR will always be in shading for all of these, or for these experiments. And then the latent heating response here is in the color shading, or excuse me, the latent heating response is in the contour, so you can see that it goes to minus 40 is our maximum of the cyclonic anomaly here, versus minus 21, right? So again, it's a 50% difference. If we compare to the full Q1, right? So now this goes to minus 60, so versus QR forces minus 20, so that's a third. A third of the total response in Q1 is due to QR. So that's a large portion of the magnitude, right? This tells us that we need to get radiative heating right if we want to properly simulate our MJO teleconnections, right? Otherwise, we're going to be missing a pretty substantial chunk of our magnitude. Okay, so we decided to take this further. We know now that the radiative heating is important. We also know that models struggle with clouds, so let's figure out what clouds are important. So what we did is we did various QR experiments. Dave showed you what the radiative heating looked like for these earlier. So we did various experiments. I'm not going to show you all of them. We removed the ice clouds and multi-layered cloud structures together and individually. We remove all liquid-containing clouds. We removed mixed phase clouds. Essentially, what happens if we remove these? What happens if they're not represented? How does our teleconnection response due to radiative heating change? And then we also did some sensitivity experiments to QR to try to understand how important that vertical structure of QR is. What happens if the lower level radiative heating is given versus the upper level radiative heating is given. Okay, so let's start with removing ice clouds and multi-layered cloud structures. So now, from here on out, all of the black contours, we represent the forcing, the response to the full QR forcing. So the full QR is in the contours, and then the individual cloud experiments are going to be in the shading. So the shading here is showing you what happens to the circulation anomalies when we remove ice clouds and multi-layered cloud structures. Now you see that we get a similar magnitude, right? The maximums are fairly similar in magnitude, but you get a really big difference over the Northeast Pacific. You get essentially that this anticyclonic anomaly ends up contained to the Western Pacific, which is really interesting. Now here we removed ice clouds and multi-layered cloud structures, telling us how important it is to include those and to make sure that they're well represented in our models. But another way to look at it is, well, this tells us just what the response is to deep convection in liquid clouds alone. And really that's just deep convection because there's not very many isolated liquid clouds that are not part of our multi-layered cloud structures. So this is really just telling you what is the role of the deep convection. What is the radiative heating associated with the deep convection force? Okay, so next slide, please. We do the same thing for MJO phases 6 and 7. So now here the main anomaly over the Pacific is in that Northeast Pacific region. And that is again where we see the impact of removing the ice clouds and multi-layered cloud structures. We get a pretty large weakening when we remove those clouds. If you compare the full QR, which is the contours, versus our experiment, where these are removed in the color shading, we get a reduction of about 40%. And we find that this shift, as well as this weakening, is entirely due to removing the multi-layered cloud structures. We find that the role of the ice clouds is essentially to magnify this response, whereas the role of the multi-layered cloud structures appears to impact the circulation over the Northeast Pacific region. So we can understand why changing the heating could have an impact on teleconnections by understanding the main balance, the main thermodynamic energy balance that we see in the tropics associated with the MJO. Due to weak temperature gradient, this is the main thermodynamic energy balance, which tells us that there's a balance between the apparent heating and vertical motion and environmental static stability. But this term here is given by the basic state, right? So this is a constant across all of our experiments. What we're changing is the heating. So if we change the heating, keep this constant, then we're going to change the vertical motion. And if we change the vertical motion via continuity, we know that this means we're going to be changing the divergence. In upper level divergence, is what is linked to forcing Rossby waves into the connection patterns. So we can see how divergence is impacted by removing these certain cloud types, right? So here you can see the divergence. This is averaged between -10 and 5 degrees north, since the MJO tends to be more centered over the southern hemisphere, especially at later phases. And here you can see longitude versus pressure. And this is for the divergence associated with the full heating given by the model. And then this is when we remove ice and mixed layer cloud structures. And you can see a substantial decrease in the entire signal, and pretty much everything on this side within the Western Pacific is largely gone. So this is a different experiment. This is removing liquid-containing clouds. So because we're removing liquid-containing clouds, another way to think about this is not only how important is it to ensure that liquid-containing clouds are well simulated or well included within the models, but also this is another way of telling you what this is the forcing from multi-layered cloud structures and isolated ice clouds. So for phases 2 and 3, you can see that at the top here, again, using the full QRs and the solid black contours. And then our experiment with the modified QR is shown in the color shading. So you can see that by removing liquid-containing clouds, which includes our deep convection, then we weaken our response by about 30%. It also tells you just how important multi-layered cloud structures and isolated ice clouds are, right? Because that's a substantial part of our teleconnection pattern that is forced by QR. We can do the same thing for MJO phases 6 and 7, right? And we see a similar weakening of our response when we remove liquid-containing clouds, right? So there's kind of a consistency of the impact of removing these clouds. Okay, so the last thing I'm going to show you here is our sensitivity experiment. So these, we were having fun with these, trying to figure out, well, how important is it that you get the vertical structure correct? Like, what happens if we have a low profile of heating versus we have a high profile of heating? And the difference is really substantial. So again, the solid contours, this is for phases 2 and 3. Solid contours are our regular full QR, and then our experiments are in the color shading. And you can see that when we have a low profile of heating, our circulation anomalies are substantially weakened. You can see significant changes in our divergence in the tropics, where you get much stronger convergence and much weaker upper level divergence. And that weaker upper level divergence would correspond to weaker teleconnection patterns. Whereas if you have a high profile, such that you have a lot of heating in the upper levels, then we get really strong upper level divergence, weaker lower level convergence, and a really strong response, right? So the heating up high is really, really important for the magnitude of these.
How does you dampen the heating?
Yeah, so I made I just used a gamma distribution to essentially weight the heating in the upper atmosphere, and it was normalized by the maximum heating of the profile. And so essentially just forcing the maximum level of heating to be either in the high or in the low. Okay, so just the last few slides here. Why is this important? So if we shift our focus to what's going on with CMIP6, this is a study from Field et al. In 2020, showing the range of long-wave cloud radiative effects within the various different models. And so these cloud radiative effects are generally highly driven by what we see in upper-level cirrus clouds in the tropics. The two bars we have here on the right-hand side are the cloud long-wave effects that we get from Ceres and Fluxemus LiDAR. They're incredibly consistent, about 28 watts per meter squared. So long-wave is heating by 28 watts per meter squared. And there's large range of uncertainty that the majority of these models are highly underestimating these long-wave cloud radiative effects. And further analysis, essentially showing clouds that you can look at the individual ice profiles. From this study in 2021 shows that this high bias that we see from long-wave cloud radiative effects is highly due to the cloud fraction that we get from high-altitude clouds, and about 75% bias in the ice water path, so extremely low ice water paths we're seeing from the models. And so that upper-level heating signal that is strongly due towards upper-level ice clouds is being highly underrepresented in the CMF6 models still. And so Sherwood et al. In 2020 was looking at the analysis from CMF5 and on to CMF6, showed that the highest uncertainty we have in terms of cloud feedbacks is really due towards tropical ample cloud area as well as the cloud altitudes. And so, again, what we're showing here, the vertical structure of ice clouds, incredibly important. Their ice properties, incredibly important. And that's really the main driver that we're seeing with our ice cloud sensitivities. And so, using these process-oriented metrics that we derived here of understanding how do individual ice clouds, both multi-layer versus individual cirrus clouds, differ and impact teleconnections can be really useful for this, for understanding how well our ice property is represented, and therefore how well could our teleconnections be diagnosed as well. So just to quickly summarize, the main bullet point, radiative heating from clouds, and even from clear sky, which we can show here, is incredibly important for diagnosing and understanding MJO teleconnections. Really, the advantage we have here is we're using vertically resolved data from both precipitation radars and cloud radars to get this, and so the locations of the cloud structures and precipitation structures are well represented within these processes. And that's critical for being able to diagnose this because we need to be able to see the multi-layer cloud structures, which are important to understand what is going on, because model parameterizations for terms of overlap can struggle to represent this. We've shown that in past studies as well. And further, from a passive sensor standpoint, these multi-layer cloud structures can sometimes be commonly defined as a thick mid-level cloud instead of a cirrus cloud. And so essentially these results are really suggesting that the model representation of MJO and the teleconnections really need to make sure they're well representing not only precipitation processes, but really nailing down those ice processes. And that will end it there.
This is a really interesting talk. I feel like, yeah, it blends a lot of what you've been thinking about in tropical meteorology with understanding kind of connecting the temperature gradient and also the importance of radiative heating. So I'm kind of curious a little bit more about the radiative heating component itself. Could you imagine scenarios ever where during the active phase of an MJO, the shortwave impact is significantly or sufficiently it's significant enough, so either from the low-level clouds or big enough cloud that it can actually lead to a negative radiative heating, even though the heating is positive, and that might actually lead to a suppressed phase of an MJO, like quicker. I don't know if that is.
Can you repeat that?
Like the relative amplitude?
Yeah, so with the radiative heating, if I'm understanding correctly, that's predominantly from the greenhouse effect.
So yeah, so in general, when you think about cloud radiative impacts, yeah, in the clear sky, long wave cooling is going to be the biggest impact. When you look at upper level cirrus clouds, you actually do get a significant shortwave effect of absorption of cloud top. And so kind of we go way back to here. So this portion here is actually mostly shortwave absorption. Because you get long wave cooling above this, but you do have a layer of shortwave absorption in these ice clouds. So it is an important component, but we haven't really separated the shortwave versus long wave. We've really just been focusing on that heating right now.
Can you go back to the figure where you put the MJ anomalies and show the radiation and the latent heat components? Like I kind of got stuck there thinking, yeah, my brain got stuck thinking there. Okay, yeah, so I think the community, I think you do agree about radiation being important, right? And I think that's consistent with seeing it about maybe like a quarter of the total heating. What I find really interesting of what you're finding at like the hypotheses, because like my eyesight, I can see it here fairly well. Is that you can see we usually define the MJO's vertical velocity structure, which you would get in WTD. It would look like that third one right over there at the bottom. And I guess I'd never really thought about, at least with these satellite people, that like that first baroclinic, so-called first baroclinic motion type of the vertical velocity. That upper tropospheric half of the vertical velocity seems to be mostly radiatively driven and not convectively driven.
Yeah.
So I guess like maybe I'm not thinking about this super well, but like I think that that's like a massive conclusion because you're not really getting the full three-dimensional structure of the MJO. You know, because like as Steph mentioned, like in order to get the dynamical structure of the MJO, you need the upper level divergence. You need to actually have like some data and background vorticity in order to create your rotation structure. So like just by looking at this, I'm kind of stumped because if you don't have that radiative heat, you're actually not getting a very deep structure at all, but you are once you incorporate the radiation, because it's barely anything above 10 kilometers. And then it's like from 10 to 15 kilometers, which you're looking here in height, but in terms of like, you know, when you look at it in height, it looks fine, right? But like, it's actually like a lot of distance that you're actually driving mostly radiatively. So I don't know like where I'm trying to like get at here, but I think that this is like a fairly big conclusion that's been kind of like not been noted much before. We usually just think that convection just makes it all the way to the Tropical cloud at 15 kilometers, and there it just kind of like shoots out the Enzo and the Cirrus clouds. But here, we're, you know, when you think about it in terms of the buoyancy and all the processes that need to be occurring in order for the clouds to descend, you're almost kind of like hinting at that you need kind of that radiative heating to get that final push up to the top of the troposphere.
Yeah. I mean, you
And
also
that's also related to the teleconnections and how that goes and changes on the jet stream. So I don't know if you guys have thought about it, if you got any comments on that. I'm just kind of like stumped here and just wanted to like comment on that.
Yeah. Well, I also do want to mention just this is the heating. It doesn't mean that the convection is stopping at that. It's just the precipitation.
Yeah, it becomes smaller, right? But like
Yeah.
still, when you add them together, you clearly see that like adding that radiative effect does the big impact is the upper troposphere.
Yeah.
Like I don't know, I just like I'm seeing it and like I'm scratching my head, you know? I'm kind of scratching my head about this, right? Because like if you think about like the dynamics of the clouds and the fact that the whole system wants to be in WTD, like almost that, you know, like a big chunk of that upper troposphere omega that you get through WTD is radiatively driven.
We can probably show you, like, we don't have it here. Do we have the divergence differences between the latent heating the QR runs?
I do, but I didn't put them in the
Yeah, so we can show you those after
Yeah.
the fact. 'Cause, I mean, you still get good, like, strong upper level divergence from
Yeah,
latent
you
heating by
do.
itself.
Okay.
It's just
Yeah.
you add that extra, you know, quarter of the overall magnitude from the radiant heating as well.
Okay,
Yeah.
Yeah.
that's still a lot.
Yeah.
But I think, the other, sorry, just the,
You saw that those were different scales though, right?
Yeah, I did see that there's a,
Yeah,
I was just
okay.
like looking at the top and the bottom.
so traditionally that heating's been backed out from the divergence profiles themselves. And that's, so to your comment, Anel, is that the interpretation of that heating has always been that it's just latent heat driven, because
Yeah.
like,
Yeah,
I guess
'cause
a different product can still have that in it.
So this is where I'm getting at, and maybe I wasn't super clear at the beginning. In order to have WTG in the first place, you need first baroclinic gravity waves that like propagate throughout the whole tropics, and they propagate really fast. The higher order remotes don't propagate as quickly. But if the radiation and the latent heat release are coupled to each other through clouds, you're not really getting that full first baroclinic structure necessarily by convection alone. When you add them together, you actually get the more realistic structure. So that affects how you adjust your WTG in the first place. So I don't know if like adding the cloud actually leads to like faster adjustment or not, but like it has more impact than just changing the upper level divergence. It actually affects how the whole system can adjust to WTG in the first place.
You showed such a nice, wonderful correlation between clouds trap infrared and clear air lets infrared out. It's really great, and it reminds me of Linson's iris hypothesis. And my question is, to what extent can you use linear inverse modeling to understand the relative contributions of latent heating and rates of heating in future scenarios. I hear, that with more vapor that you need a weaker circulation to accomplish the same thing. I don't know if that's still true.
You can turn almost any knob in here. You would have to essentially say, if you wanted to look at smaller versus larger anvils, you could either do that manually in the radiative transfer model, or you could do it by adjusting cloud fractions. You can change all the clear sky properties you could change in terms of anywhere in the vertical structures as well. And so, one thing we didn't show here is that, the clear sky signal in terms of temperature and humidity changes also has an impact on this. It's not just clouds and latent heating. Changes in clear sky also have an impact on the teleconnection effects. And so,
I think Anno is starting to get at what I think I'm getting to with this, but could you go to the sensitivity experiment for the vertical profiles?
which ones?
That one at the end.
Yes. These ones.
That one.
Just looking at how when the lower level heating is dampened, it accentuates the pattern. Does that suggest that the latent heating aspect almost acts to dampen the teleconnections? I don't know if I'm thinking about that right.
So you have to kind of be a little careful because of the way that we defined the weighting, because they're scaled by the maximum heating. It essentially makes it so that when the low level heating is dampened, it does have some increase in the upper level heating. You're kind of squishing the profile if you will. You're saying, let's just put the heating only in the upper.
Yeah, it was kind of a way to say, what would happen if the maximum level of heating, if the maximum magnitude of heating occurred in the upper atmosphere versus the lower atmosphere.
Yeah.
And vice versa. And so it was the importance of, if you couldn't get any cirrus clouds at all, everything was retrieved from the lower atmosphere, what would it look like? And essentially, kind of the main takeaway is that, the upper level heating looks much more similar to what we saw in our control run than the lower levels. So it's really like just really enforcing that upper level divergence is the biggest part in understanding this whole thing.
Upper level clouds.
And upper level clouds.
So unfortunately, we don't have time for more questions. It is a lecture for this seminar. So, but I think you can reach out to them after that. But thank you so much. Let's just do another round of applause.